In 1925, Arthur Holly Compton penned X-rays as a branch of modern physics, a work that crystallized the revolutionary understanding of X-rays, solidifying their place within the burgeoning field of quantum mechanics. Compton's influence extended far beyond the mere summation of existing knowledge. He was a principal architect of the quantum mechanical interpretation of X-ray scattering, a phenomenon now known as the Compton effect, which irrevocably altered the landscape of physics. An examination of this book requires a journey into the late 19th and early 20th centuries, a period marked by the discovery of X-rays and the subsequent unraveling of their enigmatic nature. The genesis of X-ray physics can be traced to Wilhelm Conrad Röntgen's serendipitous discovery in 1895. Röntgen, experimenting with cathode ray tubes, observed that a fluorescent screen glowed even when shielded from the direct path of the cathode rays. He correctly deduced that a hitherto unknown form of radiation, which he termed X-rays due to its mysterious properties, was responsible for this phenomenon. Röntgen's initial experiments demonstrated the ability of X-rays to penetrate various materials and to cast shadows of solid objects, including the now iconic image of his wife's hand revealing her wedding ring. The potential applications of X-rays in medical diagnosis were immediately apparent, marking the dawn of a new era in medical imaging. During the subsequent years, physicists worldwide embarked on intense investigations into the nature of X-rays. Early theories proposed that X-rays were electromagnetic waves, akin to light but with a much shorter wavelength. This wave theory appeared to be corroborated by experiments demonstrating the diffraction and interference of X-rays, phenomena characteristic of wave behavior. Max von Lau's experiments in 1912, wherein X-rays were diffracted by crystals, provided particularly compelling evidence for the wave nature of X-rays and simultaneously provided a powerful tool for studying crystal structures. William Henry Bragg and William Lawrence Bragg further refined X-ray diffraction techniques, establishing Bragg's law, which relates the angle of incidence of X-rays to the spacing between atomic planes in a crystal, a relationship expressed as n times lambda equals 2 times d times sine of theta, where n is an integer, lambda is the wavelength, d is the spacing, and theta is the angle of incidence. However, certain experimental observations began to challenge the purely wave-based explanation. In particular, the photoelectric effect, in which electrons are emitted from a material when it absorbs electromagnetic radiation, presented a puzzle. While the wave theory predicted that the kinetic energy of the emitted electrons should depend on the intensity of the incident radiation, experiments revealed that the kinetic energy depended instead on the frequency of the radiation. Albert Einstein, in 1905, provided a revolutionary explanation for the photoelectric effect, proposing that light, and by extension all electromagnetic radiation, consists of discrete packets of energy called photons. The energy of a photon is proportional to its frequency, a relationship expressed as E equals h times nu, where E is the energy, h is Planck's constant, and nu is the frequency. Einstein's theory, while initially met with skepticism, gained increasing acceptance as more experimental evidence accumulated. This brings us to Arthur Holly Compton's groundbreaking work on X-ray scattering. In the early 1970s, Compton conducted a series of experiments in which he scattered X-rays off of various materials, primarily graphite. He observed that the scattered X-rays had a longer wavelength, and therefore lower energy, than the incident X-rays. This wavelength shift, now known as the Compton shift, depended on the scattering angle. The wave theory of light was incapable of explaining this phenomenon. According to classical electromagnetism, the scattered radiation should have the same frequency as the incident radiation, regardless of the scattering. Compton, drawing inspiration from Einstein's photon theory, provided a quantum mechanical explanation for the observed wavelength shift. He proposed that X-ray scattering should be treated as a collision between a photon and an electron. In this collision, the photon transfers some of its energy and momentum to the electron, causing the photon to lose energy and thereby increase its wavelength. Compton applied the laws of conservation of energy and momentum to this photon-electron collision, deriving an equation for the wavelength shift as a function of the scattering angle. The Compton shift, delta lambda, is given by h divided by m sub e times c times 1 minus cosine of theta, where h is Planck's constant, m sub e is the mass of the electron, c is the speed of light, and theta is the scattering angle. Compton's explanation of X-ray scattering provided compelling evidence for the particle nature of electromagnetic radiation and solidified the photon theory of light. His work had a profound impact on the development of quantum mechanics, demonstrating that light could behave as both a wave and a particle, a concept known as wave-particle duality. This duality, initially perplexing, became a cornerstone of quantum theory. In X-rays, as a branch of modern physics, Compton meticulously presented his experimental findings and theoretical interpretation of X-ray scattering. The book served as a comprehensive overview of the state of X-ray physics in the mid-1920s, covering topics such as X-ray production, absorption, scattering, and diffraction. Compton's work was characterized by his attention to detail, his rigorous experimental methodology, and his clear and concise writing style. One might say his clarity resembled that of X-rays themselves, penetrating obfuscation to reveal the underlying structure. The book also highlighted the diverse applications of X-rays in various fields, including medicine, industry, and scientific research. Compton emphasized the importance of X-ray spectroscopy for determining the elemental composition of materials and the use of X-ray diffraction for studying crystal structures. He also discussed the potential hazards of X-ray exposure and the need for safety precautions. Compton's work met with both acclaim and resistance within the scientific community. While many physicists recognized the significance of his findings, some remained skeptical of the photon theory of light. Clinging to the classical wave theory, the debate over the nature of light raged for several years, with proponents of both wave and particle theories presenting compelling arguments. However, as more experimental evidence accumulated in support of the photon theory, the tide gradually turned. Over time, there was increasing agreement that light exhibits both wave-like and particle-like properties, a concept that is now firmly established in modern physics. Compton's discovery of the Compton effect earned him the Nobel Prize in Physics in 1927, solidifying his legacy as one of the pioneers of quantum mechanics. His work had a lasting impact on the development of physics, paving the way for further advances in quantum theory and its applications. The influence of X-rays as a branch of modern physics extends beyond its immediate impact on the field of physics. Compton's work inspired numerous subsequent investigations into the interaction of radiation with matter. For instance, the study of gamma-ray scattering, which is analogous to X-ray scattering but involves higher energy photons, has provided valuable insights into nuclear structure. The development of electron microscopy, which utilizes beams of electrons to image materials at high resolution, owes a debt to Compton's work on wave-particle duality. Moreover, Compton's emphasis on the applications of X-rays has had a profound impact on various fields. X-ray imaging continues to be an indispensable tool in medical diagnosis, allowing physicians to visualize bones, organs, and other internal structures. X-ray crystallography remains a powerful technique for determining the atomic structure of materials, with applications in fields ranging from materials science to drug discovery. Even today, Compton scattering plays a crucial role in various scientific and technological applications. It is used in medical imaging techniques such as positron emission tomography, PET, and single photon emission computed tomography, SPECT. It is also used in astrophysics to study the properties of celestial objects such as black holes and neutrons. In conclusion, Arthur Holly Compton's X-rays as a branch of modern physics represents a pivotal contribution to the development of modern physics. Compton's groundbreaking work on X-ray scattering provided definitive evidence for the particle nature of electromagnetic radiation and solidified the photon theory of light. His book served as a comprehensive overview of X-ray physics, highlighting its diverse applications and inspiring further research. Compton's legacy as a pioneer of quantum mechanics is secure, and his work continues to influence scientific research and technological innovation to this day. The echo of Compton's insights reverberates through modern physics, a testament to the enduring power of his intellectual contributions, still illuminating the unseen universe with the clarity of X-rays themselves.